Assalamualaikum warahmatullahi wabarakatuh. We are from group 2 that consists of me, Muhammad Umar Haziq bin Abu Bakar, and my partner Muhammad Ismail Hakim bin Mat Pison. We are from class RAS 1201D, and we are going to present the experiment about basic measurement and Hooke's law. For experiment 1, we can take a look at basic measurement. The objective for the experiment is to determine the volume and density of ball bearing and to determine the volume and density of glass block. So the apparatus that we are going to use is vernier caliper, micrometer screw gauge, weighing scale, ball bearing and glass block. The procedure for this experiment is divided by 2, A and B for micrometer screw gauge and vernier caliper. For micrometer screw gauge, number 1, the zero error determined, and then the diameter of the ball bearing measured. Note, the ratchet knob turn until a click sound was heard. Do not overturn the ratchet knob as this would cause damage to the micrometer. And step 2, number 3, step 2 repeated at least 3 times at different positions of the ball bearing. Number 4, all data recorded in a suitable table. Number 5, the actual diameter reading taking into consideration the zero error obtained earlier calculated. Number 6, the weight of the ball bearing determined. And number 7, the density of the ball bearing calculated. So for B, the vernier caliper, number 1, the whole number of small division counted on the fixed part of the caliper that are to the left of the zero mark on the vernier. This gives you the size of the object to the nearest of whole millimeters. Number 2, the first mark found on the vernier that line up with one of the marks on the fixed part of the caliper. The value of the mark on the vernier then told you how many fractions of a millimeter are needed to complete the estimate of the size of the object. Number 3, the zero error of the vernier caliper determined. Number 4, the length, width and thickness of the glass block measured by using the vernier caliper. Number 5, step 2 repeated at least 3 times at different positions of the glass block. Number 6, all data recorded in a suitable table. Number 7, the actual measurement calculated by taking into consideration the zero error obtained earlier. Number 8, the weight of the glass block determined. And lastly, the density of the glass block calculated. So we're gonna take a look at the result and data of the ball bearing. So the diameter of ball bearing for observed reading at first attempt is 15.68, the second attempt is 15.72, and the third attempt is 15.68. So the average we got is 15.69. For the radius of ball bearing, the first attempt we got is 7.84, the second attempt we got 7.86, and lastly we got 7.84. So the average is 7.85. For the true reading of diameter of ball bearing, the first attempt we got is 15.71, the second attempt is 15.75, and lastly we got 15.71. So the average will be 15.72. The radius of ball bearing, the first attempt we got is 7.86, second attempt is 7.88, and lastly we got 7.86. So the average is 7.87. And then we're going to take a look at the result for glass block. For observed reading, for length, the first attempt we got 6.5, 6.545, 6.19, and then 6.25. The average is 6.3. And the width, we got 1.83, 2.12, and lastly 2.21. So the average will be 2.05. And height, we got 9.65, 9.65, and 9.28. So the average will be 9.53. And then the true reading we got the same because the zero error is 0.0 millimeter. So the first question is calculate the volume and the uncertainties of the ball bearing and the glass block. To calculate the volume for ball bearing, we're gonna use the formula 4 over 3 pi r power of 3. So we calculate 4 over 3 pi multiplied by 7.87 power of 3. We got 2041.7981 millimeter power of 3. And then the uncertainties volume ball bearing, we're gonna use the formula n delta r over r multiplied by v. So 3 multiplied by 0.01 divided by 7.87 multiplied by 2041.7981. So we got 7.7832 millimeter power of 3. For the volume of glass block, we're gonna use the formula L multiplied by W multiplied by H. So 6.3 multiplied by 2.05 multiplied by 9.53. So we got 123.08 centimeter power of 3. For the uncertainties volume glass block, we're gonna use the formula delta V over L plus delta V over W plus delta V over H. So 0.01 divided by 6.3 plus 0.01 divided by 2.05 plus 0.01 divided by 9.5. We got 7.5147 multiplied by 10 power of negative 3. Question 2 is calculate the density and the uncertainties of the ball bearing and the glass block. So the formula for density is mass over volume. So we're gonna use the formula 16. So we're gonna use 16 gram divided by 2041.7981 millimeter power of 3. The answer is 7.8362 times 10 power of negative 3 gram millimeter power of negative 3. For the uncertainties volume ball bearing, we're gonna use formula delta M over M plus delta V over V multiplied by P. So we're gonna use 0.1 divided by 16 plus 7.7832 divided by 2041.7981 multiplied by 7.8362 multiplied by 10 power of negative 3. So the answer is 7.8847 multiplied by 10 power of negative 5 gram millimeter power of negative 3. For the density glass block, we're gonna use the same formula mass over volume. So 304.5 gram divided by 123.08 centimeter power of 3, we got 2.47 gram centimeter power of negative 3. For the uncertainties, we're gonna use the same formula. So 0.1 divided by 304.5 plus 7.5147 multiplied by 10 power of negative 3 divided by 123.08 multiplied by 2.47. So the answer is 9.6197 multiplied by 10 power of negative 4 gram centimeter power of negative 3. For the discussion, we got the volume of ball bearing is 2041.7981 millimeter power of 3 plus 11.39, and density of ball bearing is 7.75 multiplied by 10 power of negative 3 gram millimeter power of negative 3 plus minus 5.2103 multiplied by 10 power of negative 5 gram millimeter power of negative 3. The volume of glass block is 159.49 centimeter power of 3 plus minus 6.934 multiplied by 10 power of negative 3. And density of glass block is 1.9073 gram centimeter power of negative 3 plus minus 7.0991 multiplied by 10 power of negative 4. For the first table, we measure the diameter of the ball bearing using a micrometer screw gauge. We firstly determine the zero error of the instrument, in which we have determined it to be negative 0.03 mm. This means the reading of the micrometer screw gauge that we get is the observed reading. We must subtract it with 0.03 mm to get the true reading. The existence of zero error are mainly due to the fault in the instrument from wear and tear that caused it to be skewed from its original reading. For the second table, we measure the length, width, and height of glass block using a vernier caliper. We first determine the zero error for this instrument, to which we determine it knows zero error. From this information, we do not need to apply the zero error correction toward our reading. Therefore, the observed reading and the true reading for this table will be the same data. From our measurement, we have determined that average observed reading for length is 6.3 mm, width 2.05 mm, and the height is the 9.53 mm. Since zero error do not apply for this instrument, then the true reading will be the same as well. For the conclusion, the volume of ball bearing is 2041.7981 mm power of 3 plus minus 7.7832, and density of ball bearing is 7.8362 multiplied by 10 power of negative 3 gram millimeter power of negative 3 plus minus 7.8847 multiplied by 10 power of negative 5 gram millimeter, and the volume of glass block is 123.08 centimeter power of 3 plus minus 7.5147 multiplied by 10 power of negative 3 centimeter power of 3, and density of glass block is 2.47 gram centimeter power of negative 3 plus minus 9.6197 multiplied by 10 power of negative 4 gram centimeter power of negative 3.
So let's move to another slide. Sorry, to another experiment. Is it experiment hook law? Okay, objective for this experiment is to verify the accuracy of hook law. For the apparatus, we use helical steel spring with supporting stand and skid, set of slot with hanger, and third with balance. There's a graph that we used in this experiment. For this experiment, first procedure we mass of hanger and hanger are recorded and measured. Number 2, weight of the hanger calculated and recorded as W in the table. Number 3, the scale adjusts so that the pointer on the hanger is near the upper end of the scale when the hanger is unloaded. Its position as note was recorded. Number 4, Number 4. The hanger loaded by 10 gram mass. The scale reading X1 recorded. The load kept increasing by suitable increment load equal until obtained 8 data points before the lower end of the scale is reached. All data recorded W and X note. Number 5. The process repeated by unloading the same loads as in 3. New scale reading X1 recorded again for each load. Number 6. Extension of the spring calculated. Number 7. The extension force acts on the spring F for its total loads are determined. This slide represents result of experiment. Scale reading without loads at nodes equals to 0.605. For table data, the loaded mass M weak start 0 0.01 kilogram until 0.08 kilogram. From this table, we can see the extension force F in Newton is increased with extension of the spring X. For example, for 0.01 kilogram of load mass, we got extension force for 0.1972 and extension of the spring is 0.010. The second example, 0.08 kilogram of loaded mass, we got extension force for 0.8839 and extension of the spring as we got 0.04. So we can say that extension force F in Newton is directly proportional with extension of the spring X. This slide showed a analysis for this experiment. Question 1. Graph of the force causing the extension F against the extension X. So this is the graph that we plot with the axis Y with extension force F and axis X as extension X. The gradient of graph M equals to y2 minus y1 divided by s2 minus with s1, which is 0.49 minus with 0 divided by 0.23 minus with 0 equals to 2.1304 Newton meter power of -1. Gradient of the graph represents value of spring constant K. Question number 2. How much work done in stretching the spring stroke 0.20 meter? With formula F force equals to negative constant spring K multiplied with X. F equals to negative K 2.1304 multiplied with 0.2 equals to F equals to negative 0.4261 Newton. Question 3. How much energy stored in the spring when it is extended to 0.20 meter? Us equals to half K delta S power of 2. Fill in the information we have. We got half multiplied with 2.1304 multiplied with 0.20 minus 0.01. We got 0.2024 joule. Question number 4. Describe any error that may have occurred during this experiment. First, error can be happen if incorrect usage of SI units, as example, converted mass of hanger and loads from gram to kilogram. Second, condition of the spring. Make sure the spring in good condition and not rusty. Question 5. What can you describe from your result about the relationship between the extension of the spring and force causing extension? The extension of a spring is directly proportional to the force that causing extension. For example, if the extension of a spring increases, so the force causing extension is increasing too. For this discussion, from the graph extension force against extensions, we obtain gradient which is 2.1304 Newton meter power of -1. The gradient represents a spring constant K. All data shown extension force is directly proportional with extension of spring. The region that may disturb the spring and cause error for this experiment, even though the error doesn't affect the result, but we still needs to beware. For example, we need to make sure that spring in good condition. Also, make sure the spring is hang straightly. Furthermore, from the equation F equals to negative Ks, K is spring constant and X is extension of spring. Conclusion for this experiment is, from the datasheet, extension increase when force of weight increase. Hooke's law accuracy have verified to be true based on the experiment we have conducted. That's all for us. Thank you. Assalamualaikum warahmatullahi wabarakatuh.